Hello and welcome to this video. In this video, this is hopefully going to be the final video on diffraction, where we're going to look at what would happen if we swapped out the laser for just a white light source, so like a light bulb or something. Would it still show the same phenomenon of diffraction, or is that something that's specific to a light bulb, to a laser? Okay, so the thing about a laser that is important is that lasers, the light that comes out of lasers is coherent. Coherent light. Okay, now coherent means that it has the same frequency. So all of the light is of one single frequency, and all of the light has a constant phase difference. Okay, so it doesn't necessarily have to be always in phase, although for lasers they are. But coherent light in general is just that it has a constant phase difference. In the case of a laser, all of the wavelengths are all in phase with each other. Okay, this is why lasers are so powerful, because if we have all of the light that's in phase, we're constantly getting constructive interference. So we're constantly getting really bright lasers transferring loads of energy. Now, the light that we also have from lasers is monochromatic. Okay, so monochromatic light just means light of a single wavelength. Okay, so in this case, we've only been putting through red light. Could have been green light or blue light, it doesn't really matter what color. As long as there's only one single wavelength of it, it means it's monochromatic light. Okay, which you can kind of tell from the word, because mono meaning one, chromatic meaning color. So monochromatic means we've just got one color, which is one wavelength. Now, if we were to replace this light source for a light bulb, so just a regular household light bulb that's just emitting all white light. So white light, we should know, is just a mixture. So white light consists of multiple wavelengths. Okay, which means that all of our equations that we have, so having d sine theta is equal to n lambda, and also having w is equal to lambda d over s, they're both specific to the wavelength that we have. So if we were going to enter a bunch of different wavelengths, we're going to end up with a bunch of different fringe spacings or angles that they're going to diffract at. So we'll see a pattern that's going to look quite strange. And so what we actually see is in the setup, we have to change something slightly. White light is not coherent light, so we need to add a single slit beforehand. So this is the white light. These are the wave fronts with a difference. Actually, it probably wouldn't be smart to draw wave fronts if we're going to get loads of different wavelengths. So let's say the white light just passes, let's say we just have one single wave. We first need to put it through a single slit. What that's going to do is cause some slight diffraction, and that slight diffraction, the single slit, is just here to make the light coherent. Okay, so it makes the light coherent. So it basically focuses it in so that all of the light that we have at these, I'm just going to use a double slit, could still be a single slit, or could still be a diffraction grating. I'm just using a double slit because I think it'll feel like it's the easiest to conceptually grasp. I should probably move the position of the slits up a little bit to here. But yeah, so we put the white light through a single slit first. That makes the light coherent so that when it passes through these secondary slits, we can see a diffraction pattern being formed. Now, drawing this diffraction pattern is going to get quite tedious. So instead, I'm just going to get a image from Google Images, and then I'll talk you through it. Okay, so here we have an image that shows the contrast between what's at the top. So at the top we have a monochromatic light source. Monochromatic light source, and at the bottom we just have a white light source. Okay, now we can see that the places where we have fringes in the center, we still have a central white fringe. This is because all of this light that we have is still going to travel the exact same distance to get to that center, which means that all of the light is going to converge to be there again. So we're still going to have a white light at the center. So we still have a white central fringe. It's then after that white central fringe where we start to see this splitting of color. So you'll notice we have all of these smaller things. This image would not have been taken from a double slit. This is probably going to be more like a diffraction grating interference pattern. And so we can see very slightly we have smaller, fainter maxima in these minima positions. But what we see then is that first things on both of these sides is we get the blue that then goes into green and then goes into a little bit of orange and then red, and then we have minima, and then we'll see that the further away we go, the more we'll get confused. So it's, if we went over here, for example, so in this region, it's very difficult to see the difference between what would be a fringe and what's a minima. Whereas the closer we get to the middle, we can kind of tell that these positions are where the minima are, and this are where the minima are. But as we go further out, because of this change in the angle, we have a much bigger difference between the fringe spacing of all of these things. So why does blue come first and then go to red? It's based on the wavelengths. So if you remember back to primary school, thinking about the colors of the rainbow, we said that the colors of the rainbow start as red, orange, yellow, green, blue, indigo, and violet. Okay? Meaning the shortest wavelengths are violet. Okay, so the longest wavelengths at the top, shortest wavelengths at the bottom. So the shortest wavelengths are violet, meaning if we have the smallest wavelength, we have the smallest fringe spacing. So the smallest gap between these two is caused by the smallest wavelength. Also the same for the smallest angle. So the angle that forms this spacing here is going to be the smallest because the fringe spacing, the wavelength is the smallest. Okay, so they can usually ask you to describe what would be seen on an image when we look at white light diffraction, and you would say that you have a white central fringe, and then you have a spectrum of color starting at violet, going through to red, and then that is a repeating pattern that we see as we move outwards. So you'll see that we go to red, we go darker, then we go to blue again, through to green, through to orange, red, back to blue, green, orange, red, and so on. Okay. So this is the idea of white light. There is a very short little extra part that is going to mix the two together, so we can now relate back to looking at quantum when we were looking at electron diffraction. So I'm going to do a very short bit on electron diffraction here, and we'll see what the difference between these things is. Okay, so electron diffraction, if we were to observe it, the process of electron diffraction is different. While we could put it through the same kind of slits that we've been putting all of this other light through, what we actually do in practice is electron diffraction gets put through a graphite sheet. Okay, so we fire some electrons from an electron gun, we accelerate them, so this is the anode that's going to accelerate them. The anode has a little bit of a slit in them. The slit is not where the diffraction happens. Okay, that's just to accelerate them. After here, they have a thin sheet of graphite. Okay, now the thin sheet of graphite is acting as the slit. Okay, and that is because graphite structure is hexagonal. So it looks something like this, where all of the vertices would be carbon atoms. Okay, you might remember this from GCSE or even A-level chemistry. And what's going to happen is the electron is just going to come straight through this gap, right, in that hexagon, and that is what's going to cause it to start spreading out. Okay, so the gaps between atoms are acting as the slits here, but we'll notice all of the other slits we've had have always looked like a complete vertical line. Because this is almost a circular slit, the pattern that we see is also going to be circular. So what we call them are concentric fringes. And those fringes, when you see them, look a little bit like this. So we still have at the very center a bright white maxima. You'll see in this case they've probably accelerated these electrons through a very high potential, because you can still see green light where all of these dark fringes are, but the actual fringes are where you can see this like very bright lines. Okay, so these are the actual fringes, and all the bits in between are the minima. Now again, they're circular just because the shape that we've put them through is circular. You could literally make the diffraction slit whatever shape you wanted. You could have them as like letters of the alphabet and then try and decrypt which ones are going to be which shapes when on a fluorescent screen. And all of this stuff will follow the exact same phenomena as all the regular diffraction, except now we've just got electrons. The reason they produce light is because they're on a fluorescent screen. Okay, so this is a fluorescent screen. So when they collide, they transfer all of their energy, and that energy is then emitted as photons. Okay, and so that's why we see the light. Okay, this is then going to wrap up diffraction. Hopefully all of this makes sense. Try and have a go at a lot of practice questions, because this is going to be a very mathsy based topic. And thank you for watching.